Have you ever asked yourself how car infotainment system, which is based on Android Automotive, is getting loaded? Every time you start your car, something incredible happens behind the scenes before the screen lights up with music, maps, and applications. A complex chain of software and hardware is already racing into action. In just a few seconds, Android Automotive must boot, load services, and bring the head unit alive. Today, we will break down one of the most common AOSP interview questions, which is Android Automotive booting sequence. Welcome to my boot sequence series, in which we are monitoring booting sequences of different platforms and operating systems. To be able to see the steps and the wizard in the car head unit, there are many software should be loaded and executed between car ignition and screen glowing. At the beginning, after power up, we can observe normal Linux booting sequence steps. Because if we check Android layers, we will see Android uses the Linux kernel as its core engine to handle all low-level tasks like process scheduling, memory management, and hardware abstraction through drivers. From the other side, Android replaces almost the entire traditional Linux user space. It uses its own C library, which is called Bionic, and its own runtime. This makes Android not a traditional Linux distribution, but rather a unique operating system built on the Linux kernel. As normal Linux booting sequence, the first software triggered is the manufacturer ROM Bootloader software, which starts running from CPU ROM, and it's responsible for initializing minimal hardware and clocks. Also, copy memory loader or MLO software from predefined memory like SD card into SOC RAM. Then ROM bootloader pass control to memory loader, which is getting executed from RAM memory of the SOC. Next step, we can see MLO up and running to perform DDRAM initialization and prepare to load U-boot from SD card to DDRAM. Finally, MLO pass control to secondary bootloader or U-boot. After U-boot is loaded in DDRAM, it performs hardware-specific initialization like display, memory, and storage, as it initializes more hardware like Ethernet and other peripherals. Besides that, U-boot reads environment variables to locate boot partition and loads boot.image component, which contains Linux kernel, device tree blob, and RAM disk.image. As boot.image component is loaded to DDRAM, also U-boot setup kernel command line to boot Linux kernel. After that, control moves from U-boot to Linux kernel. After control moves from U-boot to Linux kernel, kernel parses device tree blob which loaded into RAM by U-boot to perform full hardware discovery and initialization. Then, kernel will be in a need to load system.image, which exists in ext4 partition. But kernel don't have the initial root file system running, so how kernel will load system.image, which is the heart of Android operating system? To answer this question, kernel will mount RAM disk.image to create an initial root file system and launches the first stage init, which mounts system.image from ext4 partition. Then hands over control to the second stage init from system.image that completes the Android boot process and start all system services. And now it's clear how kernel is able to load system.image. But what is the main kernel functionalities? Kernel performs hardware initialization as it parses device tree blob to detect and configure memory and other peripherals. Also, kernel loads and initializes built-in drivers including ext4 file system driver and many other things like memory management, process management, file system mounting, and interrupt handling. As mentioned previously, our init process is divided into two stages. First stage, which mounts system partitions and provides transition to SELinux. SELinux loads security policies before handing off to second stage init. Second stage init is the final stage, which initializes properties, parses.rc files, and sequentially start to call services like logd, service manager, service flinger, media services, and ultimately execute Zygote to begin the Android framework initialization. After the native service initialization completes, as we mentioned previously, Zygote is launched. As one of the last main class services, Zygote preload Android framework classes and resources. Also, Zygote forks to create system server for core Android services. Then, Zygote enter a listening loop to rapidly spawn application process on demand. As conclusion, Zygote serving as the parent process of all Android apps and system services. System server. The system server is forked from Zygote as the first and the most privileged Android process. System server initializes the core system services, including ActivityManager, Package Manager, Window Manager, and Power Manager. It's clear to see that system server builds the first foundation that runs all applications and control how Android works. ActivityManager. It is the central service within system server. Also, it controls how all Android applications run and switch between each other. So, ActivityManager manages application lifecycle, memory usage, and security to keep everything running smoothly. So, we can say that ActivityManager is the central Android service that manages the complete lifecycle of all applications. Launcher. It is a default Android home screen application. Launcher serves as the user's primary interface to the system, providing app drawer access, widget management, and home screen customization, while coordinating with ActivityManager to launch applications and manage the user's workflow through an intuitive visual workspace. Finally, boot completed comes after launcher app is visible and the entire system is ready to go. Boot completed informs other applications that launcher is running and system is up. Let's take practical example to understand the relationship between app launch, system server, ActivityManager, and Zygote. ActivityManager serves as the central traffic controller for all activity transition within Android. When a user taps an application icon like messages or contact, the current application sends an intent to system server, where ActivityManager service evaluates the target. And here we have two possibilities. First case, application is already running in the background. Then ActivityManager service simply routes the intent to its existing process. Second case, if the application is not already running, ActivityManager service asks Zygote through Android OS process to fork a new process. The new process starts execution at activity_thread.main. Once the process is created, its PID sent back to system server. Then, ActivityManager service issues a schedule launch activity, which tells the new process to create and show the new application UI. At the end and after launching our Android system, in my case I launched it through emulator, we can see that all of what we have mentioned in this video is a simplified description of booting sequence from system power to application launcher. I am Alaa Al Najjar. Wish you a good day and meet you in next video.